All right, so now we're trying to find the pH of a weak base. Pretty much the same routine as finding it for a weak acid. First off, how do we know this is a base? A couple ways. One, if we look at the formula, this NH2, this is sort of like a part of a ammonia type group, that usually is going to be able to gain an H plus to be a Brunson-Lowry base. But the real way, if you're not sure, look, they give you Kb, that's telling you this is a base. So let's write out the reaction for this. If this is a base, it's CH3, NH2, and usually we're just going to react with water. And if it's acting as a base, it is going to be receiving an H plus from water, which is going to make it CH3, NH3 plus. And when it mixes with water, water losing an H plus is going to make it OH minus. That's kind of why this is basic. It's raising the concentration of OH minus in the solution. So we'll set up our ice chart like before. Our initial change in equilibrium, our initial concentration of this is 1.2 molar. And our initial concentrations of these are always going to assume are 0. And how much is this concentration of CH3NH2 dropping by? We don't know, so we'll say it drops by X. Remember, we can ignore water for this because it's a liquid. We just don't need to include it in our expression. But if our CH3NH2 drops by X, these are going to have to rise by X. So our final concentrations are going to be 1.2 minus X, X, and X. And ultimately, we want to find this value of X because that will tell us the concentration of OH minus, which will allow us to find the base. So now it's an algebraic problem again. I know the value of Kb. It's 4.4 times 10 to the negative 4. And the expression for that is going to be, I guess I skipped that part, but it's going to be this product, so X, times this, X, over this concentration, 1.2 minus X. There's no coefficients in this expression, so I don't have to worry about squaring or cubing anything. So I'm just solving for this equation. And just like with the weak acid, we can assume X is going to be really, really small. This K value is not as small as the last one, but compared to the concentration that we're given, it's small enough that we can pretty much assume that this is not going to change much, that it's pretty much just going to be 1.2, which is a nice algebraic assumption. You don't have to make it. You could use a quadratic equation. We just will not be doing that here. So we solve, and we will get 5.28 times 10 to the negative 4 equals x squared. I just brought the 1.2 over, squared that, and then if I take the square root of both sides, I will get x equals 0.023 about. And that is the molarity of, that's x, so it's the molarity of this chemical, which we don't care about, as well as the OH minus, which is what we want to know. So how do I find the pH from that? Well, I can't directly. I can find the pOH. So the pOH is going to be the negative log of this value, 0.023. So I'll first calculate the pOH, which turns out to be 1.63. That's the pOH. Remember, the pH and the pOH have to add up to 14. So if I subtract this from 14, I get the pH is 12.36, I guess, when I did my rounding, or 37, depending on how you handle it. And that is the pH. And I do a spot check. I remember this is a base, so the pH should be above 7, which it is. So that is it. So this is how you find the pH of a weak base. Pretty much the same way as a weak acid. Just remember that you get pOH at the end, and you have to do a quick conversion. So until next time, I'm Derek Genova. Have a delightful day.